with circular motion. A block is released from rest at position A, slides with negligible friction down an inclined track around a vertical loop and along a horizontal portion of the track as shown above. The block never leaves the track. Which of the following is true of the net force on the block when it's at position C? When it's at position C, it has the force of weight going down, but it's turning. And weight is not going towards the center or away from the center. And so it must also have a normal force that's taking it there. And so it needs to be going down and to the left. So E is our appropriate choice. Planet M of mass M orbits a star of big M, and you can see where introducing ellipses and center of masses are making sense here, because we're saying that M is much smaller than big M. So that means that we can say that R is just going to be the distance between their centers, or the center of mass can be considered to be at the center of the large M. True statements about the planet's orbit include which of the following? The orbital speed equals 2 pi r over t. The gravitational force does equal gmm over r squared. And if r were greater, t would be greater. So again, we know that the relationship is that the period squared is proportional to the radius cubed. So if this gets bigger, does that get bigger? Yes. So it would be all three of them. And you can see how that plays into Kepler's third law. An object attached to one end of a string moves in a circle at a constant speed. Which of the following is correct? It is accelerating as it moves. This is not true. It does require a force. Something without a force is going to go straight line. It would move tangentially, so it's A. A new planet is discovered that has twice Earth's mass and twice Earth's radius. On the surface of a new planet, a person weighs 500 newtons on Earth would experience a gravitational force of. So, gmm over r squared. G is not going to change. The person's mass isn't going to change. But we're saying that the new planet has a mass that's twice, so I'm going to put it at 2 for that. And it has a radius that's twice, so I'm going to put it at 2 for that. And so that's going to give me 1/2. So if they weighed 500 newtons on Earth, they would weigh 250 on the new planet. A compressed spring mounted on a disc can project a small ball. When the disc is not rotating as shown in the top view above, the ball moves radially outward. The disc then rotates in a counterclockwise direction as seen from above, and the ball is projected outward at the instant the disc is in the position where shown above. Which of the following best shows the subsequent path of the ball relative to the ground? So it is going this way. The ball would like to go that way, so when I push it out, it's still going to have that tangential speed. So an object in motion in straight line wants to stay in straight line motion. A child has tied a toy at the end of a string which whirls the toy at a constant speed in a horizontal circle at path of radius r. The toy completes each revolution of its motion in a time period t. What is the magnitude of the acceleration of the toy? Acceleration is v squared over r. So if we're saying that v is the circumference over t, then we would have 4 pi squared r squared over t squared r. And I could cancel out 1r. So 4 pi squared r over t squared. A steel ball is supported by a stick, rotates in a circle of radius r as shown above. The direction of net force acting on a ball when it's in a position as shown indicates which of the following. Things do not go in a circular motion unless there is a force directed towards the center. There is a force up, which is normal, and a force down that's gravity, which means in the y direction. they would balance out and be 0. Each of 5 satellites makes a circular orbit around an object that is much more massive than, again, so we don't have to worry about center mass. The mass and the orbital radius of each satellite are given below. Which satellite has the greatest speed? So we're going to have GMM over R squared equals MV squared over R. So V is going to be related to radical GM over R. So the mass of the planet that's orbiting it, I'm sorry, the mass of the satellite that's orbiting it doesn't matter. Only the mass of the planet matters, the gravitational constant, and how far you are from it. Because this is in the bottom, making this smaller will make that bigger. And we see this in the planets. So Pluto still hasn't made an entire orbit of the Earth since it was discovered. It hasn't had a year yet. So as you get further out, it takes them longer and longer. And that makes sense of comets too. We have comets that, you know, the short-term ones, like Halley's Comet, 86 years. Like that's a long time for a short term. 67, a satellite of mass m and speed v moves in a stable circular orbit around the planet of mass m. What's the radius of the orbit? Again, we're setting our force equal to our F net and getting R by itself. So little m's cancel out. And it's C. A planet of mass of planet X is 1/10 that of the Earth, and its diameter is 1/2 that of the Earth. The acceleration due to gravity on the surface of planet X is most nearly. Acceleration due to gravity is the force of gravity divided by mass. So where I had GMM over R squared, I'm just going to have GM over R squared. So the universal constant's not going to change. The mass is going to be 1/10. And if the diameter is 1/2, the radius is 1/2. But that 1/2 is going to be squared. And so I'm going to have 1/10 divided by 1/4, which would be 4/10. So if it is 10 on Earth, it's going to be 4/10 that, or 4 on this new planet. A race car is moving around a circular track of radius 300 meters as shown above. At the instant when the car's velocity is directed due east, its acceleration is south. So when it is east, its acceleration is south. That's the only way that works, right? Because if it was going that way around it, when it's east, its acceleration would be north because the acceleration has to be centripetal. And it has a magnitude of 3 meters per second squared when viewed from above. The car is moving clockwise. And we need the velocity. So we say that A is equal to V squared over R. So V is going to be radical of A R. So this is 3 is our given acceleration, and 300 is our radius. So it looks like 30 is the best answer. 2 artificial satellites, 1 and 2, orbit. I'm going to take a break here.